Dear students, in this unit we are going to discuss about torsion. Before that, you know what is shaft. Shaft is said to be a torsion when equal and opposite forces are applied at the two ends of the shaft. The torque is equal to the product of the force applied and the radius of the shaft. Due to the application of the forces at the ends of the shaft is subjected to a twisting moment. This causes the shear stress and shear strains in the material of the shaft. Derivation of the stress produced in a circular shaft subjected to torsion. Before the derivation of shear stress produced in the circular shaft, the following assumptions are to be made. First, the material of the shaft is uniform throughout. The twist along the shaft is uniform. The shaft is uniform circular section throughout. Cross section of the shaft which are plane before and after twist. All radii which are straight before and angular after twist. Okay, consider a bar of length L and the radius R fixed at one end and the other end is free, is subjected to a torque of T as shown in figure. Then the C is the modulus of rigidity or G we can use. And the toe is the shear stress induced at the surface of the shaft due to torque T. Therefore, the strain is equal to the distortion per unit length, that's d dash divided by L. Therefore, d dash is equal to L pi. The arc length is equal to R into theta, that is equal to L into pi. Therefore, the shear strain is tau divided by C. So, substitute the pi value in the equation 1, we get pi tau divided by R. The strength or maximum torque transmitted by a circular solid shaft. The strength of the shaft means the maximum torque or maximum power the shaft can transit. The maximum torque transmitted by the circular shaft is obtained from the maximum shear stress induced at the outer surface of the solid shaft. That is, tau is proportional to R. Consider a shaft subjected to a torque T. Also consider a small elementary circular ring of thickness dr at a distance of R from the center as shown in figure. Let tau is the shear stress induced at the surface of the shaft due to the torque T. R is the radius of the torque. Q is the shear stress at the radius R from the center. Therefore, the area of the ring dA is equal to 2 pi R into dr. Then the Q is the shear stress induced at the radius R from the center of the shaft. Then the Q by R is equal to 2 by R. Shear stress is denoted by Q is equal to tau by RR. Then returning force on the elementary circular ring is equal to shear stress acting on the ring into area of the ring Q into dA. Q already known and dA is equal to 2 by R into dr. Therefore, R divided by 2 into 2 by R square into dr. dt is equal to tau by R into 2 by R cube into dr. Then to find out the torque, we can differentiate the dt from 0 to R. We get T is equal to pi into tau d cube divided by 16. Next, the torsional equation. From the equation 3.3, we know that c theta by L is equal to 2 by R. But from the torque transmission on the shaft on equation, tau is equal to T into 16 divided by pi d cube. So, substitute the tau value in the equation. C theta divided by L is equal to T into 16 divided by d by 2 into pi into d cube. C theta by L is equal to T divided by pi by 32 into d power 4. Here, pi by 32 into d power 4 is the polar moment of inertia of a solid shaft. Then the above equation becomes C theta by L is equal to T by J. Similarly, the polar moment of inertia of a hollow circular shaft is equal to pi by 32 into d power 4 minus small d power 4. Capital D is the outer diameter, D is the inner diameter. From the equation, we know that T by J is equal to C theta divided by L is equal to tau by R. Torque is transmitted by the hollow circular shaft. Consider a hollow circular shaft of outer diameter capital R0 and the inner diameter capital Ri is subjected to a torque capital T. Take an elementary circular ring of thickness dr at a distance r from the center as shown in figure. Let small q is the shear stress, d is equal to 2 pi r into dr. The shear stress of the elementary ring is obtained from the shear stress ratio is equal to q by r is equal to r by r0. The q is equal to r divided by capital RD. Okay. Then find the turning force on the elementary circular ring is equal to shear stress acting on the ring into area of the ring equal to q into dA, which is equal to r divided by r into x to 2 by r square into d square. Now turning moment due to the turning force of the elementary circular ring, find out the dt and differentiate the t value from r inner diameter to outer diameter. We get t is equal to pi by 16 tau into d 0 power 4 minus d I power 4 divided by d of outer diameter. Next one is torsional rigidity. The product of modulus of rigidity into and the polar moment of inertia of a circular shaft is known as torsional rigidity, which is denoted by the letter capital K in expression this C into J. The torsional rigidity is also defined as the torque required to produce a twist per unit length in radian. Therefore, Cj is equal to TL by theta. The polar modulus is nothing but polar moment of inertia to the radius of the shaft. Then power transmitted by the shaft is equal to power transmitted once the torque T for a solid or hollow shaft is obtained. Power transmitted can be obtained. P is equal to 2 pi nt divided by 60 watts, or P is equal to T into omega. Next, saving of material and weight of a solid and hollow shaft. The percentage of saving of material is equal to area of solid shaft minus area of hollow shaft divided by area of solid shaft into 100. Percentage saving in weight formula is weight of solid shaft minus weight of hollow shaft divided by weight of solid shaft into 100. Okay, these are the numerical problem. We can find the torque produced in the solid shaft or circular hollow shaft using the derived formulas. Okay. Compute the values. If you have any doubt, clarify with me. Thank you.